It's my pleasure to welcome back Jeffrey, which has been coming for, what is about the fifth time?
Something like that, yeah.
So,
COVID makes everything hazy. I can't remember.
Yeah. But I mean, if you go to his personal page, it's a photo from pre-COVID. I love that Jeffrey, who is an important person, please look at his bio. But he was telling everyone at SC, I don't know, 23 or something, Multicore World was my last international travel before COVID. And he keeps saying and saying, so I was, okay, I can use that as a marketing expert.
Yes, absolutely.
Thank you very much.
Yes, thank you. It's happy to be back. There we go. There we go. Okay, very good. Thank you, Nicholas, for that welcome. I think Christchurch is wonderful here. The park, Hagley Park over there is fantastic. It's great to be back. I had to amend my slides slightly since Dan and Simon and others talked about some of the topics, and so that's why Nicholas was harassing me up till yesterday to get my title in. So I hope you'll enjoy it. So the short story is that, as you've heard already, we have unprecedented computing demand. And I love this. I'm a computer scientist. I really couldn't ask for anything more at this time. The idea is that we really need to generate more power. And at Oak Ridge, we don't understand what the problem is. You just build more nuclear power plants. That's the answer, right? Surprisingly, there are weird supply chain issues that a lot of people like me didn't even know about. IEEE Spectrum just had a special issue on the transformer shortage worldwide. And it's gating all of these data centers because there aren't enough transformers. Who would have known?
These are power grid transformers.
Yes, right. Yeah, not the model, not the AI model, right? Yeah. And then we have things like carbon, climate, and of course the expense to worry about. With the market cap of these companies, nobody worries about that right now. And then, we're excited because we've really turned to understand why we need to improve the energy efficiency of our systems. And, implicitly, we've all kind of been doing this. Whenever you think about Moore's Law and Dennard scaling and the progress we've made over the past few years, past decades, in fact. If you look at the Kogi report, really the stretch goal was in 1 exaflop and 20 megawatts. People were talking about 1 gigawatt or 2 gigawatts for an exaflop system, and so we really met that. This explicit focus on energy efficiency is really falling down into two topics. Really, in the short term, specialization and integration, so like chiplets plus heterogeneous integration, 3D stacking, things like that. And then a longer term, what's even more exciting is people are really starting to think about new computational paradigms like analog computing, neuromorphic, quantum, things like that. Now, the downside is when you get all that hardware complexity is somebody has to program these systems. And we are trying to push the agenda that AI can be the answer here. And so one of the things that I'm going to talk about is some recent work we're doing to port applications to new architectures using AI that really minimize the requirements of the user who's doing the porting. Also, you've heard of Fortran, right?
I did.
Yes. I'm on a graduate fellowship panel, and they're asked, the students that apply, what programming languages they use and expect to use. Last year, out of about 50 of them, one of them mentioned Fortran, and nearly all of them mentioned Python. I think maybe one of them mistakenly omitted it, probably because it was so popular they didn't think it was worth mentioning. But that's where we're going, right? And so the big worry is, what do we do with all those Fortran codes? And of course, it's Dusty Deck and things like that, and nobody wants to work in it. So finding a workforce to do it is the hard part. Things like optimizing workflows. And we're going to talk about how we're doing some LLM prompt engineering and fine-tuning to try and make that easier. So the obligatory slides, you've seen some of these already. The demand for gigawatts in data centers, this is a McKinsey report. You'll see, this is 2023, about 55 gigawatts. If you take the way, and it's kind of confusing, these highly paid consultants came up with this chart, but this is like the lower bound and this is the upper bound. The upper bound is, you'll need, 300 gigawatts of power if you hit that upper prediction. And that's significant. To see that, I love this chart the Washington Post put out about 2 months ago, I think. So anybody flying to Dulles in the US, it's near DC. It's a big airport there, international airport. You can see it right there. Well, they've experienced a huge growth in data centers around that area. And this is a plot of that. They actually call it Data Center Alley. I think the red dots are the old data centers and the blue dots are the new data centers. And if you take that box called DC12 and you zoom in on it, you see kind of the 2014 version. If you take that same area and look at it 10 years later, these are all the new data centers in just that box that I showed you there. So it's real. It's not hype to some degree. And so what are we doing at Oak Ridge? So at Oak Ridge, one of the things that I mentioned earlier is, we believe in nuclear power. And so there's a lot of effort underway to advance SMRs, or small modular reactors. In fact, we are on the trajectory right now to put a small modular reactor at the old TVA Clinch River site. It was part of the Manhattan Project. You're not going to build subdivisions there, so why not put a reactor there, right? And so that will be about 300 megawatts of power once it's installed and up and running. But, there's a lot of interest nationwide about this. And even up there in the right-hand corner, you'll see there's a new uranium processing facility being built at Oak Ridge to generate uranium for nuclear power plants. So the second one I mentioned was, and this again was surprising, I'd been hearing rumors about this from our facilities team for a while, but IEEE just had a special section in their IEEE Spectrum magazine about this. Some of these transformers that you need for data centers can be backlogged by 4 years, right? If you have a high voltage line coming in and you need to take that down to 3 volts essentially, or 1.5 volts, you need those, and there's no real way around it. In fact, Nadella said power was their limiting factor now. It's not chips. It's the fact they can't get enough power into the facilities that they're using these in. And so that's interesting. At Oak Ridge, we have some activities going on there to design new types of transformers, including things like 3D printing the internals of a transformer. So, okay, so that's kind of some of the interesting stuff that's going on right now. Who would have predicted this in the 5 years ago? It's exciting. So one of the things that we did at Oscar last year was we actually had a new workshop because they've got a new focus, and it is to focus on energy efficiency. And the idea here was to think about how you get energy efficiency out of the system. And it's not just about developing a new memory cell or a new transistor. It's about looking across the whole stack to understand if your algorithms can be improved, if your software can be improved, or if you can actually use new paradigms for this. There were actually 2 workshops with this one, analog computing as well as neuromorphics. So they're thinking out of the box. They're thinking about new computing paradigms altogether. Antonio here in the audience helped with the analog computing workshop, and I've been part of Oscar for 20 years, and these types of architectures have not really been considered before. They're being considered now. If you look at the topics that were discussed at the workshop, the main ones were things like algorithms. So thinking about new types of algorithms like randomized algorithms, mixed precision, how to use some of the AI data flow hardware effectively to do computational science. It's interesting to think DeepSeek was really an algorithmic achievement, right? That was the thing that led to a huge drop in stocks, not just NVIDIA, but even the nuclear stocks dropped, right? They were down 20, 30% in the same time period because people thought, hey, we don't need all that compute. Software, there's a great paper called There's Plenty of Room at the Top, and Science, I believe it was 2021, that shows that really, we need to take more care in optimizing our codes to make them perform well and be energy efficient. There's also this problem of the extreme heterogeneity. How do we write code for these new systems? Everybody can't afford an ECP to go out and port code from one architecture to another. How are we going to manage that? And then hardware, as I mentioned earlier, really in the short term, the CMOS trajectory is really stable for the next 3 to 5 years. But the longer term, thinking 10, 15 years, we really need to start thinking about new hardware paradigms. The data management and workflows, Raphael mentioned that some earlier. There's really a need for that, just even down to the storage devices themselves, as well as measurement and modeling of energy. It's surprising how a lot of the simulators that you have, architectural simulators, do not really model energy well. And it's also surprising how few details you can get out of a lot of the data centers about where exactly their energy is going. So hopefully, those are some of the things we're going to address in this program. So thinking about energy efficient computing hardware. So many of you know the whole GPU move, and that's been really inspired by this domain specific computing. I think this is just going to accelerate. We wrote a report about 5 years ago called Extreme Heterogeneity. And the whole idea was that you're going to have all these domain-specific accelerators on a chip. It's your job to figure out how to use them. But TSMC has embraced this philosophy, as well as people like Intel and AMD, you see there. They use chiplets, which are essentially stock IP that they design, and they mix and match them on the substrate to get the performance for the certain workloads that they want. TSMC has got, a lot of capability to do this. They've already created a lot of packaging facilities where you can take things like the substrate and basically put whatever you want on it. And it can be different materials, different processes, things like analog, digital, photonics, memory, and kind of weave them together to get the performance you want. And that's their trajectory going out to get to 1 trillion transistors on a package, right? And so again, I think this is done, right? This is the way we're going to buy new systems. Now, the real question is, will that get us where we want? And if you've looked at Blackwell and the specs on Blackwell, it's pretty shocking. And it's not just the price, it's the TDP or the thermal design point and some of the other specs that you have with that chip. So let's think about new paradigms, like I mentioned earlier. And I took this chart back last year and started thinking about what all kinds of options we have when we build a computer. And what you see here is really the star indicates things that we're using today. We're using flash for storage. We've still got a little bit of disk and tape out there, optical, electrical, not really photonics. And then you've got all of these non-von Neumann models that people have access to. And then at the lower level, there's a huge amount of work going on into new types of main memory, as well as compute. Graphene, carbon nanotubes, all of those things. And they do have the promise of providing better energy efficiency. And so one of the things over the past few years that we did at Oak Ridge was we had a project called Abisco. And this is a busy chart, so let me walk through it. The idea was that you could design a chiplet that did spiking neural networks, and that spiking neural network would all be processed in the analog domain. And so what we had to do was involve people from the applications area, and that was for a high energy physics sensor, come up with the algorithms to implement the spiking neural network, and then map that onto an architecture. The architecture, meanwhile, was being designed from basically the ground up, where we were looking at brand new materials. I'll say a little bit more about that, and then putting them together in devices that would actually compute things like the spiking neural network. And so another way to look at it is on this slide. So if you take the data that's being generated by the LHC detectors that we're targeting, they have about 1 billion channels generating about 1 petabit per second. All that data comes flying in. Right now, what they do is they feed it off to a bunch of FPGAs. The FPGAs have to filter it out. Ideally, you could filter all that out in the sensor, so you could get about 99% of it before it gets converted to digital, so you don't waste all that energy converting, managing, and storing that digital data. You just filter it out right in the sensor. And so what we did was we took some of the data and created a spiking neural network that gave us a much better performance than what we could get with a deep neural network or convolutional neural network. And if you know anything about spiking neural networks, what you basically have to do is encode the data, send it through, and then you have a SNN configuration that tells you whether it's an article of interest or not. And so there's just a snapshot of what our final spiking neural network looked like. It's compressed, so these are all the hidden nodes, these are all the input nodes, and these are the 2 output nodes. And it's basically, yes, you have a particle of interest, and no, you don't have a particle of interest. And so that's what the logical SNN is deciding. And so this is just a logical representation of that network that we can simulate and work with, but we wanted to actually try and build it. So when we get down to that architectural level that I mentioned earlier, you can have a digital design or an analog design. And this is assuming you have that chiplet framework where you have some kind of processing element, and you probably have a CPU, GPU, some memory, maybe photonics, and then a component that's a neuromorphic component. The digital one is made in traditional CMOS. Nothing fancy there. That's something we could fabricate today. The analog is a new material, and it's made by taking these materials, and they have resistance that is tuned with the charge that you put across the terminals, and then the charge stays permanent, and it affects the resistance of the actual device itself. And I'll show you more about that in a moment. But looking at the digital option, you have, we called it NeuroSpark, and this is the digital design. And this is kind of a block diagram of what a spiking neural network neuron looks like. And that's what it actually looks like in the digital design that we have. You have the input spikes coming in, and then you have things like ADCs and summations and charges and a threshold check, and then an output. And that's the way you basically fabricate one of those. If you look at the design flow we're using for that, it's a traditional design flow. And essentially what we do is target an FPGA now. So we can run this on an FPGA that can be plugged into any board that we currently have. And it's important that we meet the timing. As I mentioned earlier, those high energy physics experiments are pumping out huge amounts of data. In terms of about every 1 to 10 nanoseconds, you have to be ready to take data coming out of the device. And so with our FPGAs, we had to try different settings and different configurations, and we ended up with a couple of those designs that actually meet that latency criteria. The lowest latency we hit was 6 nanoseconds. The good news is, and there's a lot of detail I'm omitting just because of time, but the idea is that we're targeting this SNN for actually building it in a digital chip. And what we're working on now, we got some additional funding to actually try and take it to fabrication. And so this digital component, we're going to add to an existing test chip that's being planned for FY26. And part of that is taking the HLS components that create the FPGA and move them over to the ASIC tool chain. But that's a lot of fun. We haven't, the group is, a few people in the group have built chips before, but this is new for our entire group. So it's a lot of fun to do this. So that was really the digital option, right? That was the standard flow. That's something that we can send to Global Foundries or TSMC today, IMEC, wherever, and they can send it back to us using standard tool chains and standard materials. The new paradigm that I was talking about earlier is what we really set out to explore here. And, analog computing is not new by any stretch. I mean, you can find papers at least that go back to the 1950s. It can be much lower power because you're not converting things to digital, holding them in specific, like a von Neumann configuration where you have to fetch the data. It's just processed on the fly. There's a lot of existing algorithms, believe it or not. There's spiking neural networks, simulated annealing, FFTs. There's really quite a list of algorithms that people have already explored here. Now the challenges are noise, right? Because it's not really being error corrected. Precision. Most of the analog work is not at 64-bit or 32-bit or 20-bit. It's usually down in the 6, 8, and 4-bit precision category. And then there are things like scalability and interfaces that you have to think about. So what we're doing here is combining CMOS with this analog design in a 2.5D design. And so the current design looks like this. We have a RISC-V chiplet and a memory chiplet, and that is essentially plugged together, and so you have several of these chiplets. The chiplet has an interface, and then it has this neuromorphic clusters. And, it's really scalable how many of these you can fit. It's just parameterized, so you can scale them up and down based on the final material characteristics and geometries. And inside of that neuromorphic element really turns into a crossbar. And so that crossbar is made up of new types of materials. And if you haven't studied this, there's a really clever things you can do with this crossbar. If you look at the crossbar, and this is one that was actually fabricated, it's vanadium dioxide. It's called electrochemical RAM, and it's just like it sounds. You have a crossbar where you have these input voltages coming in across the rows, and then you have currents that flow out of the columns, and you read those out. But essentially, the mathematics you get out of this is it's just a bunch of vector products across those voltages. So you can do things like, Saxby or spiking neural networks. Remember, all those neurons had all those inputs, and they had weights associated with them, and then they had an output. That's exactly what those columns represent there. And the G's represent the weights. And so that, in turn, each one of those weights is being represented by that vanadium dioxide I mentioned earlier. Now, there are memristors. There are, a number of them, hafnium oxide and some other things. But what we were looking at was this new idea called ECRAM that came from battery technology, and it has some properties like programmability that the memristors don't do so well. If you've studied memristors much, one of the things that's difficult about them is they're hard to program. So if you need 1,000 ohms in that G spot right there, you have a possibility that you'll get 10,000 when you try to program it. So a lot of them keep repeating until they get a value they want, which wastes energy and things like that. So anyway, again, I'm really excited about this. We have some prototypes. We've been trying to map our SNNs into these analog crossbars. We're finalizing some PPA estimates there and the peripheral logic, and hope we can do a prototype in 27. We don't have the funding for that right now, but we're going to aim for that prototype. And so I want to stop there for a second, and I know that was the hardware part, but just to recap, the idea is we want to look at new models. That analog crossbar can compute in parallel what would take thousands or potentially millions of instructions to compute if you were doing them on a normal architecture. And it all is happening continuously. So that's where you get a big energy savings. And so that's the idea there. Since I'm switching slightly to a different topic, does anybody have any quick questions on that?
Yeah, Jeff, I know we don't have John Shelf with us. He would be an advocate for the open chiplet ecosystem.
Sure.
I was just wondering what you would be, what your, I think I was seeing real chips. So what kind of chiplet form factor were you using? Is it OCP or something like that?
Well, what we're doing right now is just starting that process. So we have the IP for the FPGA, or the tool flow is for the FPGA, and so we're generating bit streams for the FPGA. The next step is to do exactly what you say and get a PDK that includes the chiplet form factors and other constraints, and then start mapping it into a chip design flow.
Next question. No one wants to know anything about chiplets.
Yeah.
Different flavors. Mint, coconut.
It's awesome. There's so much going on now,
Chiplets. I invited a gentleman called Bapi Vinakota.
Uh-huh.
Now he works for the government of the government.
Yes.
I had to send an invitation to the government, so they know everything about me. And they barely will allow me to make an online presentation. I'm wasting time in order for you to take another option for a questions.
All right, that's
no
fine.
more questions. Keep going.
I'll speed through this part, but this is probably something that you'll all relate to. And in fact, I'm surprised we haven't seen more AI. I mentioned this age of software in an era of extreme heterogeneity. We've been talking about this since we started doing all the GPU work. It's getting much more difficult to program the systems. Could AI be to the rescue, right? That's the question. So we really, in ECP, I was a low-level manager in ECP, but I oversaw many of the programming models. Surprisingly, the programming models didn't converge during ECP. They diverged, right? We had new programming models, new domain-specific languages. SYCL became exciting. We had things like Cocos that really grew during that time frame. So it was challenging. And the problem is most of those solutions were incomplete, buggy, and lacked a strong ecosystem, right? And so you had users trying to use them, and it was really challenging to stay in front of that. And as I've described, we've got more complexity on the way. The pace of change is also accelerating. There used to be a day when you would have a system on the floor for 10 years and use it. Now that may be 2 or 3. And I would argue that we don't have the budget or the people to track this rate of change, right? And it's not only, even if we could afford the people, like with Fortran, we can't find people who will work on it, right? They're like, that's a dead end. I don't want to spend time on it. And Fortran's a great language, it hands down, but you just can't find people. LLMs, so very good. So how can we prepare? And so, what we're thinking is this. We have, want to improve productivity of LLMs. We don't want to necessarily make it automatic. And so what we want to do is make it much, much easier using LLMs to program these systems. And, a lot of people are doing this, but they're not focused on scientific computing or perhaps some of the architectures we're focused on. And it's not necessarily to generate perfect codes. It's to get you close, and then you tweak it. So the techniques we've been looking at is first prompt engineering. And this is where, you know what this is. You just send a prompt to the system and it gives you an answer. And if you don't like the answer, you tweak the prompt a little bit. Then there's multimodal prompting, and that's really where you maybe have some Fortran code, and you put in that Fortran code, and then you say, give me some CUDA code that does the same function. And then finally, there's the fine tuning, and that's what we've been working on most recently, where we take some of the open foundation models and fine tune them for things like OpenMP or Cocos or CUDA, and then you can use those in your prompts and you get much better results. At least that's what we're seeing. So we're calling this Chat HPC. It's really building on this and this whole ecosystem. We've got a paper we're working on now, so what you're seeing here is really a work in progress. But the idea is what I mentioned earlier. Everybody who programs for us would sit down and they would have this capability right next to them or plugged into Visual Studio or whatever their favorite editor is, so they can do this. You know, what is the motivation? Of course, we have some of the data that we want to focus on that may not be on the internet. You know, the responses are sometimes incomplete that we get when we just look at the LLMs that are out there now, like Chat HPC. And then there are things that we want to do, like can we just use some of the finer grained LLMs like Llama Code Llama, and fine tune it to do what we want. And so it's a lot less data and a lot less to manage. And so that's one of the things we've been doing. As I mentioned, just speed up a little bit. We've been doing this fine tuning instead of training. In fact, for our Chat Cocos that we've created, it takes about 20 minutes of adding the new data and tuning the model. We've been looking mainly at Code Llama for that, and I'll show you some results here in a second about how well that's going. The infrastructure, we're not using Frontier or anything. We're using a DGX box to do our fine tuning. And so it's not the exorbitant systems that you hear about or see. We actually have, like I mentioned, some Jupyter and VS Code plugins that actually help you do this. Been doing a few other things. There's the architecture. What we actually really started out with was Julia. And so we wanted to have people in writing code in Julia and then making use of the Chat HPC infrastructure to go out and generate kernels, to take a kernel that already exists and parallelize it, or to take code that you had from another program like Fortran code and convert it to Julia. Since then, we've added some other flavors to it, and that includes things like CUDA and OpenCL. So just to give you a flavor for that, here's an example of the thing we've done, Chat HPC prompt. You know, you say CUDA to set the context. Give a code that computes the multiplication of a matrix A with a vector X and stores the result in vector Y using CUDA. This is the response that we get, which you can take and run and test very easily. And this is what the infrastructure does now. It can actually create unit tests for this so that you can do basic testing against the responses that you get back. Then there's automatic parallelization, where in Julia, if you're familiar with Julia, what you want to do is actually take this piece of Julia code right here and then create a version that you see over there that will run on the CUDA extension to Julia. And it works, okay? And I'll show you some results in a second about how correct it is. And so we're looking at, a lot of these. And, ultimately, someday you would batch these together so they would not have different packages for each one. But we have, looked at BLAS, Cocos, Iris, some of the tools like Adios, and we have fine-tuned LLMs that target those different programming models. And so just to talk about Chat BLAS really quickly, the idea there was, and again, this was looking at just AI generated. If you go into Chat HPC now, or Chat GPT, and ask for a BLAS routine, what do you get? And so Chat BLAS was an effort to try to make that happen. just as a makefile would be a list of prompts that get executed against the LLMs. And so here's an example. So here's a Saxby, right? And so what it does is there is no code. We're not providing any code, right? We provide a prompt that gets fired off to the LLM of your choice, and then the result comes back and gets inserted into a make-build system that, like I mentioned earlier, is tested. And then you get some idea of what, whether it meets basic correctness checks. I've got some diagrams over there to show you what it looks like, but we have, dozens of routines that we have done this way. And what you see over there is an example of the 0 to 1 is not the best metric, but it's a metric we came up with to show you just with prompt and prompt engineering how correct the codes were. So we did OpenMP, CUDA, and HIP. And what you see here is, and what some of these things mean, like 0.6, it means that it compiled and it ran, but it didn't pass a test. Which one is it? 1? It went from 10 to 1 in like 2 seconds. That's okay. Yeah, okay. I'll try and speed up. But the surprising thing is that, we expect this to get better, right? The LLMs are getting better. And right now, many of the routines that we were looking at, we already get correct. Like the OpenMP 4.0 version, all of them checked out and were usable. And then there's kind of more detailed prompting that you need, but some of this may be able to be automated. So when you do prompt the system, you get something interesting and correct out of it. And then, since I'm in a hurry, we did fine tuning, and in some cases, we got, and this is just out of the paper, so you can go look at this if you like. In many cases, we got performance that was on par with the vendor library, and in some cases, it wasn't good, and we're working on those. But in some cases, we were a lot faster than the vendor library, and so that was equally interesting. I'm not going to talk about this since we're running short on time. The takeaway here is prompt engineering can really improve the correctness of the codes, but doesn't guarantee 100% correctness. The fine tuning that we did elevated the correctness, and we saw it, we could get up to 100% correctness on the work we were doing if you engineered the prompt on the fine tuning. I'll stop there. We do have additional work on converting legacy Fortran code over, and the comment I'll make there is it's really effective for Fortran, and I think it's because it's a simpler language, but it makes it very easy to take that Fortran code and convert it to Julia or some other language, and it's been surprisingly good. And so I've talked about demand, I've talked about the hardware project and kind of the new computational paradigms, and then finally some of the fun we've had lately with AI, and we just see nothing but lots of opportunity here right now. So I'll quit there. Thank you, Nicholas.
Well,